Here we come. We're coming down the home stretch. We're working our way through the 2019 free response questions from the AP Calculus AB exam. We're on question number 6. This is the very last question. So we're putting the finishing touch on things. You're dreaming of your 5. You're getting a step closer to your 5. And I just want to encourage you to keep working hard because I know you're going to do it. As we dive into this question, I think you're going to see I thought A and B were very student friendly, and then I thought C and D got a little bit goofy. So we're going to try to work real hard on those when we get there. So we got a couple of interesting conditions here right out of the gate. Let's see if I can minimize this picture a little bit. There we go. All right. So I'm reading the introductory paragraph here, and they said, okay, we've got 3 functions, and none of them have been given to us explicitly. We really don't know who F is. We don't know who G is. We don't know who H is. We do know that they're all twice differentiable functions. The significance there is that means they're all continuous, which is really, really nice. We've got this interesting piece of tidbit that G of 2 equals H of 2 equals 4. So they intersect at least right there. That's if you want to make a note on your paper, all this really means is that they intersect. Now, here's where it got really interesting. They said, here's this line that is tangent to both the graph of G and the graph of H when x equals 2. So let's pretend, I just drew 2 hypothetical random graphs here. Let's say that point right there is x equals 2. Okay, so you'll notice the 2 graphs, and I guess it doesn't matter at this point who's G and who's H. Maybe we'll call this guy G and this guy H. So they both equal 4. And they both happen to have the same tangent line. They have the same instantaneous slope right there. And I went ahead and I drew a little tangent line at x equals 2. And you can see how that line appears to be tangent to both the purple G function and the green H function. Just as a quick sidebar, that tangent line lies below G, not because he's increasing or decreasing, but because he's concave up at that particular moment. And that same tangent line lies above H, again, not because H is increasing or decreasing, but because H is concave down. So that's another concept that pops up a lot on these exams where you're trying to determine whether a tangent line lies above or below a curve, and it all traces back to that curve's concavity at that point. So here we go. Part A wants us to know or to determine what the value of H prime of 2 is. In other words, what is the slope of H, particularly at this moment right here? Well, all you got to do is look at this tangent line. What's the slope of that particular line? The slope is going to be 2/3, so therefore the value of H prime of 2 is equal to 2/3. There really shouldn't be any more work than that. You want to be real cut and dry there. All right, let's shimmy on into part B. This is not a bad problem either. If you haven't already attempted this one, go ahead and try this one on your own. The derivative of A is going to require product rule. Let's think of 3x cubed as the first of the 2 functions and h of x as the second function. So the derivative of A is going to be the first function multiplied by the derivative of the second function plus that second function multiplied by the derivative of the first function. So we've got a really nice product rule there. And we're going to evaluate this bar at 2. So substituting a 2 is going to make, 24 times. Now, h prime of 2 is what we just found to be 2/3. Okay. Now, h of 2 is also given to us, and that was 4. And then I believe this is going to be 36. So just cleaning this up a little bit, we're going to get 16 plus 144, which turns out to be 160. So the good news is, you've got 4 points total out of 9 already, which is nice. I think part A was worth 1 and part B was worth 3 in the College Board rubric. So that gives us a good foundation to work off of. And let's go see how many more points we can get. You've probably heard of, I hope, and probably done a lot of work with L'Hopital's rule. This is going to put just a little different twist on anything that I've seen with L'Hopital's rule before. So they've introduced us to this new function, h, right here. Of course, that function is going to be undefined at x equals 2, they said. X cannot equal 2. Now, they just said, instead of saying, hey, evaluate the limit, they just said the limit can be evaluated using L'Hopital's rule. And what that means is you're running into what's called the indeterminate form. So when they said you could use L'Hopital's rule, They're basically saying the limit as x approaches 2 of h of x is 0 divided by 0. And so if we examine the numerator really quick, I think we could confirm that substituting a 2 for the x does produce 0. Now, we're also guaranteed that this limit for the denominator is also going to equal 0. And that's really, really handy. So substituting that 2, we know that 1 minus f of 2 quantity cubed has to equal 0. In solving that algebraically, we could prove that f of 2 must be a 1. So that's kind of half of our answer right there. Now, the second half of this question says we need to try to find f prime of 2. So we already found f of 2. We got to try to find f prime of 2. And this is a little secret ninja trick right here. Do you remember how they said back in the original that all those functions f, g, and h, they were all twice differentiable? Well, when we say that a function's twice differentiable, we're also guaranteeing that it's continuous. So any function that's differentiable implies that it's also continuous. Now, what's so special about continuous? Where are you going with this? Well, when something's continuous, we know that the limit, and I'll just do it, we'll do it with respect to x equals 2 here. The limit as x approaches 2 of f of x must equal the exact value of f of 2. That's guaranteed to be true anytime something's continuous. And we already know that f of 2 is equal to 4. Whoops, I'm going to call timeout real quick. I got to rewind. These should be h's right here. Let's focus on h. All right. And since we already know that h of 2 is got to equal 4, we could conclude that the limit as x approaches 2 of h of x also has to equal 4 based on the condition that h is continuous. Okay, so how does that help me? Well, again, let's go ahead and apply L'Hopital's rule right now. And real quick refresher, all we're going to do is we're going to derive the top half to get 2x. We'll derive the bottom half using some really nice chain rule here. So it's going to be -3. Don't touch that inner function yet. It's just going to subtract 1 to make it a 2 there. Now multiply by the derivative of that inner function. That's some really nice chain rule there. This has to equal 4. So what I'm going to do is I'm going to go ahead and substitute the 2 for x and cross multiply. And that is going to give me 4 equals -12. Now, f of 2 we already know is going to be a 1. Okay, so that's not a big deal. And I think we're going to prove that f prime of, whoops, that's going to be a 2 right there. This is going to be a 2 right here, is going to be -1/3. So kind of a twofold answer here. F of 2 equals 1. And f prime of 2 equals -1/3. The big kickers there were you knew this expression right here had to equal 0 if L'Hopital's was even applicable to begin with. And then we also knew that once we did apply L'Hopital's rule that the limit had to equal 4 based on the fact that we were differentiable, which meant we were continuous, which meant this value here had to equal the limit. Now, as we wrap things up here for D, we're going to get into a theorem that I can't tell you off the top of my head the last time I saw this theorem assessed on an AP exam. So we're going to dive into it right now. So I'm going to give you a chance. Feel free to hit the pause button and read this to yourself slowly a few times if you need to. But at the end of the day, what we ultimately need to prove is whether or not k is continuous at x equals 2. So never lose sight of that. And how are we going to prove whether k is continuous at x equals 2? We're going to try to prove that the general limit as x approaches 2 for k of x is equal to k of 2 itself, the exact value. If we can prove that those two values are equal to each other, then we will have successfully proven that k is indeed continuous at x equals 2. So how are we going to do that? So here's what the squeeze theorem looks like. And I first grabbed a picture of probably something the way you'll see it in your textbook. So this is the real formal part. But basically, we have the same initial condition. You've got one function's always smaller than the other two. One function's always in the middle of the other two. And the third function's always bigger than the other two. And they said, so let's say this. Let's say the limit of the smaller one as x approaches a is equal to the limit of the largest one as x approaches a. So they're both equal to some number we'll call L. So that's the smallest function and the biggest one are both equal at that point. Okay. then as long as that's true, then we could guarantee that the limit of that middle function also equals L. And I think that it totally is very intuitive in the sense of if G's got to stay in between them and the other two are already equal to the same thing, then that third one's got to be equal as well. This next little clip here, I want to give credit where credit's due. I took this from, let's see, right here. I want to nagwa.org, a great website, a lot of good information. So if you're looking for additional resources, I encourage you to go there. Just wanted to give them a shout out. So basically, we're saying, okay, pink's always the smallest, gold's always the biggest. This green one is going to squeeze its way in between them. And as the gap starts to narrow and narrow, he's got to go bang, he's got to go right through that intersection. So there's a right when x equals a, they all intersect each other. And then we'd say all three limits have to be equal to each other. All right, so here's what I wrote out a few of my notes, so I get my thoughts on paper here. But here's how we're going to walk through it, and we're really focusing on right now. We're going to try to prove this first half here. Find, what exactly is the limit as x approaches 2 for k of x using the squeeze theorem. So they said that g and h were both differentiable. In fact, they said they're twice differentiable. So that implies that g and h are both continuous. That's a big deal, continuous. So because g is continuous, and since g of 2 is equal to 4, that implies that this limit as x approaches 2 of g equals 4. The same could be said for h, using a very similar walkthrough process. One implies the other. Now, because these are both the same, and you can go back and reference that definition of the squeeze theorem, we could conclude by the squeeze theorem that the limit as x approaches 2 of k of x must also equal 4. They're all equal to 4. They're all equal to the same thing. So we've kind of checked off that left side. Now all we have to do is prove that k of 2 is also equal to 4 so we could say k is continuous. Now, again, think of this statement right here. They said k is always going to be in between or equal to g and h. So let's just draw our own little picture here maybe. Let's say, okay, here's h, that's always up here. Maybe g's always down here. And then we'll throw in the k is always going to be kind of floating in between here. And he's got to squeeze through there. There's our k function. So he's always in between or equal to both g and h. So there's a nice visual to have as we go to try to wrap this up. So to wrap up this bear, all I really said here at this point was, since k is always in between or equal to both g of x and h of x, then k of 2 must equal 4. You could even say, you might have even maybe squeezed in here, and because g of 2 equals h of 2, which equals 4, then k of 2 must equal 4. Then finally, at the end of the day, we could say k is continuous at x equals 2 because the limit as x approaches 2 of k of x equals k of 2, which equals 4. Woo, baby. There we go. So thanks for hanging in there with me, guys. Hopefully this helped. Go ahead, share it with your friends. We'll continue to spread the word and build this great math community that we're all a part of. And we're going to get a step closer to that magical 5.